Well, thanks y'all for joining this webinar that we're doing today, and um, maybe we'll have people continue to trickle in as we get started. But you likely know that this is our webinar about enhanced geothermal energy or enhanced geothermal systems. This technology that's really been taking more front and center stage recently as developers are putting projects in the ground and showing what it can do and how it can be potentially part of the clean energy system of the future. So we've invited Dr. Roland Horn here to talk with us about this topic. He is the Thomas Davies Barrow Professor of Earth Sciences at Stanford University and is also the director of the Stanford Geothermal Program. So we're going to have him talk for a little bit, and we'll talk a little bit about what the context is for geothermal in Montana, and then we'll jump into some questions and answers. So with that, you can take it away.
Great. Thank you very much for the introduction. Can you hear me okay? Great.
Yeah.
Right, let me share my screen. So, thank you all for attending. I'm here to talk to you, as you heard, about enhanced geothermal systems. And I titled my talk somewhat tongue-in-cheek, Are we there yet? Because we've been actually working towards enhanced geothermal system for more than 50 years. But maybe we're almost there. So, just a quick introduction to geothermal itself, for those of you who may not be totally familiar with it. The whole business that we're in geothermal is to take hot water and or steam out of the ground, put it to some use, and then having extracted the heat from it, put it back in the ground again. That's done in two contexts, actually, either for generation of electricity, which is mostly what I'm going to talk about today, which is probably the more interesting application, or in some cases they use the heat directly for space heating, district heating, or industrial heat. But anyway, the business we're in is much like resource recovery from oil and gas, or for that matter, for resource recovery from groundwater, drilling wells, taking fluid, putting fluid back. And in certain parts of the world, geothermal is a very important part of their energy mix. So you can see here from 2023, some countries, Kenya is number one on this list, take almost half of their national electricity from geothermal. And there are plenty of other countries that take, a quarter, sometimes almost a third. Um, and geothermal has been growing worldwide. If we look at the last 20, 25 years or so, from 2000 to 2020, the total installed capacity as well as the total generation of electricity from geothermal worldwide basically doubled. However, um, the target for geothermal production in IEA's net zero scenario is actually three times what it is today or what it was in 2020. And we, of course, are now over here somewhere. I don't know if you can see my pointer. We're not getting there quick enough. So although geothermal is expanding, it's expanding linearly, whereas some of the other sources like wind and solar is actually expanding exponentially. So the question is, how can we get to where we want to be? I should also mention, talked about the world. In the Western states, actually, geothermal is very important too. So, state of California, we generate about 6% of our electricity from geothermal. And the state of Nevada next door actually is currently producing almost 10% of its electricity from geothermal. So, we have, together with those other countries like Kenya, Iceland, New Zealand, Philippines, etc., very advantageous geology that allows us to get to those kind of figures. Um, but we're not getting there quick enough. If we want to go to tripling of the geothermal capacity, we've got to do something more. And that's where we introduce enhanced geothermal systems. So in order to have geothermal production in the manner that I showed you from Kenya and California and Nevada, you need basically three things. You need heat, you need water, and you need permeability. You've got to move that water through the hot rock, extracting the thermal energy and bringing it to the surface. And heat is basically everywhere if you drill deep enough. At what cost is something that we need to address a little bit later. Um, and water is almost pervasive in most of the planet as well. So in the original invention of enhanced geothermal system in the 1970s by Los Alamos National Lab, they originally called it hot dry rock. Um, but that was a concept or a term which was quickly abandoned because nobody ever found a dry rock at 5 kilometers depth. They're all pretty much saturated with water. And there are some dry rocks, but they're very, very uncommon. But the thing which a lot of places are lacking, given that they have heat and water, is permeability. And one of the things which is a little hard to convince or for petroleum engineering, oil and gas development people to get their head around with geothermal is that the quantity of fluid that you have to move is absolutely gigantic. So the value, the dollar value of a barrel of hot water, if you want to call it that, is about 1/50th of the dollar value of a barrel of oil. So people do make money with energy extraction from geothermal. But what it means is you've got to move 50 times as much water up to the surface. Um, and therefore, the permeability we're talking about is not, um, permeable sandstone. We're talking about massive fractures through hard rocks for the most part. So if you don't have those fractures, the idea basically you make fractures yourself using hydraulic fracturing, which is something, of course, that we know how to do from shale developments. Now, if we look at the target for EGS nationwide, this is just the lower 48, but both Alaska and Hawaii are quite attractive too. Um, this is a map that we made at Stanford of the temperature at 7 kilometers depth. And what you can see on the color bar on the right-hand side um, is an indication at 140 degrees centigrade. And that's basically the kind of temperatures that are needed for commercial operation of a electrical power station generating from geothermal hot water. So what you can see then, that sort of straw yellow color covers most of the lower 48. Obviously, it's more attractive here in the West um, and the Gulf Coast, and actually, got some oranges up in your part of the country too. So not so bad. The question is, again, at what cost? And that's something I'll come back to a little bit later on. So, as I mentioned, this is an idea that was invented 50 years ago at Los Alamos National Lab, and there've been a dozen or so EGS projects worldwide. And the question you might reasonably ask is, well, why aren't we doing this already? And the reasons are actually listed here. There are some things that we have to overcome in order to make EGS work. And that's what people have been working on now for quite some time. The basic issue is that you have got to get a large volume of water in contact with a large volume of rock. So unlike oil and gas, pulling the fluid to the surface is not the objective. It's the heat that's contained in the fluid which you're actually after. So if you were simply to bring the water to the surface and extract its energy, that would be insufficient to make an operating project. You've got to be able to recycle it again and again. So in the case of EGS, the fractures through which it circulates are the fractures that you create yourself. And therefore, you have to be able to create a sufficient area of fractures in a sufficient volume of rock in order to sustain a production for 30 years or so, which is the typical life of a project, that being the commercial life of the power plant itself. Okay, so that's the first issue. The second issue is that you can make a lot of fractures, but you have to put them in, you have to distribute them in a certain way so that they don't short circuit. If you have one big fracture which goes from an injector to a producer, all of the fluid brushes down that one fracture, um, it doesn't get in contact with sufficient rock, and basically it cools down very quickly. I'm talking about a couple of weeks or months. So that's not um, useful. And then finally, as I mentioned before, the quantities of fluid, the rates of fluid production that are required are enormous. A typical geothermal well that makes money today of a conventional type is producing of order 50,000 barrels per day, or in the units that I'm going to use in this talk, about 80 kilograms per second. So that's kind of our target, if you want to think of that. And then finally, not so much of a technical issue, but as something of a license to operate issue, public relations issue, is induced seismicity. So anytime we have subsurface operations, oil, gas, groundwater, um, geothermal also, we have the possibility of induced seismicity. For the most part, it is, I mean, we always have induced seismicity when you have underground fluid movement, but typically not to the point where people can feel it. And it's once it becomes large enough for people to feel that it becomes a problem. And that has been the case in a couple of EGS projects in the world, two of them in Switzerland and one of them in Korea, where they produced quite large earthquakes and basically shut the project down. So coming back to the issue of flow rate, so I mentioned, 80 kilograms per second is a sort of a ballpark figure that we should look at. This is, a normal geothermal well. I'm labeled this as hydrothermal. That's kind of conventional geothermal without fracturing. So these are the kind of wells that are produced in Kenya, places like that. And you can see this particular one is producing 70 kilograms per second total flow. And, people make money with those kind of flow rates. That's about 45,000 barrels per day. But if we start looking at some of the EGS projects that have been conducted around the world, there's been a number of them, as I said, about a dozen. Initially, they were kind of government research projects before they started to become commercial. But then you can see here this particular one in France at a place called Soultz. They had an EGS project there, and they achieved 8 kilograms per second sustained. So they're sort of an order of magnitude less than they really needed to be. Here's one from a project in Japan. Again, there are lots of lines here, but if you look at the pink one, they also achieved, at best about 8 kilograms per second. So once again, not really enough. And over time, people kind of got better at this. This is basically the first commercial EGS project that was put in operation in the world uh, in Germany. It's actually not so far from Salts, and they achieved 70 kilograms per second flow. And with 175-degree water, they're producing about 3 megawatts. It's a somewhat controversial issue as to whether or not we call this an EGS project, because if you look at the temperature profile here on the left, you can see that actually this has this vertical section. This is kind of half conventional and half EGS. They only fractured one of the two wells, and the other well had its own permeability to start with. So it is enhanced, but it's not the kind of complete from scratch enhanced that we imagine for EGS. Nonetheless, it has been operated since 2007. And if we look at a map of the Rhine Valley, you can see actually there are several projects. There are 5 in total. Is Landau and Salts that I've already shown you pictures of. 3 of these projects are in Germany and 2 of them are in France. And if we look at the summary of their production, I mentioned Landau and Salts. Insheim is a little larger, 4.8. And Rittershofen is interesting in that it doesn't produce electricity at all. It supplies heat to a starch factory, which is close by. But to put that in context, the relationship between thermal megawatts and electrical megawatts, that's what the E and the TH stand for, is roughly, order of magnitude 10 to 1, because, a power plant of the type that are typically used can take 10 megawatts thermal and make 1 megawatt electrical. Well, what you can notice about this list is that although these are operating commercial projects, um, they're very small. 1, 3, 5 megawatts. These are not, game-changing power plants. They were used for exploring the technology, but they don't really make much of a dent in the power market. There's a picture of Rettershofen. There's a picture of Stolz. So Rheingraben is where the most activity has been in Europe, but we've had EGS projects in the US as well. In fact, quite a number of them, starting with, this is going sort of back in time. Number 10 was the initial project started in the 1970s at Fenton Hill by Los Alamos. And there's been a number of attempts along the way, but I draw attention to the ones with the asterisks here, which are the ones which are currently active in the US right now. And in particular, this one at the top, Blue Mountain, which is in Nevada, is an EGS project developed in 2023, which produced 63 kilograms per second for a total electrical output of 3.5 megawatts. So 63 kilograms per second is now in the ballpark of what we're looking for. So this is a true commercial project. And I'll talk about some of the others in a moment. So Forge, the second one on the list, is actually a DOE research project. It's not intended to make power, but it's intended to explore the technology. They looked at 5 different sites across the US and ultimately down selected to one, which is in Milford, Utah. So that's the one which is currently active. So in Utah Forge, you can see what they did. They drilled a number of vertical wells to delineate the system. And then they drilled these 2 long reach wells, 16A and 16B, which go about a kilometer or so as their EGS wells. See a cross section in a moment. And one of the striking things that there were many useful outcomes from the Forge project, which is still ongoing. One of the most important ones is the experience they had with drilling. So this well, the blue one up at the top, 5832, was the vertical well that they drilled first to delineate the system, and then they went on to drill their deviated wells. And this is a plot of drill depth as a function of drilling time. And what you can see as you go 1, 2, 3, 4, the amount of time that it took them to drill the wells got substantially less. And that's of enormous importance for geothermal because half the cost of most geothermal projects is in drilling. So in this case, they cut their drilling time down, by a factor of 3 or 4, and that makes an enormous consequence to the cost of the project. And the methodology by which they improve the drilling rate also has produced a lot of impact, in the geothermal industry as a whole. So this was a huge advance, a big step forward. Now I want to take a small step aside here and introduce you to the members of the Stanford Geothermal Program. This is our research group, as it was actually in 2016. And I'll show you this picture because it's colorful, but also because I want to draw your attention to this gentleman in the middle, whose name is Jack Norbeck. So that was Jack Norbeck in 2016, and this is Jack Norbeck today with another Stanford graduate, Tim Latimer. And these 2 guys, who are, I don't know how old they are, early 30s probably, started a company called Fervo Energy, which has made a lot of waves in the geothermal community and the energy community in general. And what Fervo did was to take a look at EGS in a new way that people had not done before. And Tim Latimer had been a drilling engineer in West Texas, drilling shale plays. And so he decided to try the methodologies from shale oil, shale gas into geothermal. And there are basically 3 different things that he adapted, transferred over from oil and gas to geothermal. One of them is horizontal wells, which people had never tried in geothermal before. The other one was plug and perf completion. And again, that was unusual in geothermal because geothermal is typically drilled in hard rocks that doesn't require full casing, the perforation. And then finally, he used propped fractures, which again had not been done in geothermal before because geothermal previously had been imagined to self-prop because the rocks are so hard. But they did all three of those things, and they did them, first of all, in Nevada. You can see on the map here, that was the Project Red. That was the one on the top of the list I showed you before. And here you can see what they did. First of all, they drilled this vertical well to delineate the system and to pick the temperatures that they wanted for their production, as well as to delineate the stress direction so they knew the direction to drill their horizontal wells. And then they drilled the two horizontal wells, a total of about a kilometer long, and did multi-stage fracture between them. Again, sort of typical for shale developments, but completely revolutionary for geothermal. And this is a top view and side view of what they did. This is the microseismic cloud, which they used to delineate the fractures. And this is an important piece of information. Also, this is a production log of one of the two wells. One well had 16 stages of fracturing and the other one had 20. And up at the top here, you can see the flow out of each of the 16 stages. And although it's not uniform completely, it's pretty good. Most of the stages were producing something, and none of them were producing that gigantic amount. And you remember that was one of the points that I listed before, the need to avoid short-circuiting and distribute the fractures over the large volume of rock, which is what they successfully did. And they put those two wells into commercial operation in October 2023, so they've been running for about 2 years now. And they supplied hot water and steam to the existing Blue Mountain power plant, which was close by, which was basically short of fluid, more or less because the reservoir itself was so tight, which was bad for conventional geothermal, but good for EGS. So then Fervo moved on from Nevada to Utah, and they actually intentionally moved right alongside Utah Forge. So here's Utah Forge right here, the DOE project. And Fervo came in and bought up the leases right across the fence. And they started drilling systematically their horizontal wells across the countryside. And as of last month, they had drilled 22 horizontal wells in Utah in this project, which they call Project Cape. And if we look inside view, you can see here, here's Utah Forge. Their wells are not actually horizontal. They're drilled at 65 degrees, which they did intentionally so that they could more easily get tools in and out of the wells, that being one of the reasons for the project. Here's Fervo on the left-hand side. And interestingly, on the right-hand side, there is a third geothermal field, which is called Blundell, which is a conventional geothermal project, which has been operating since the 1980s. And if you look at these red lines, which are the isothermal contours, you can see that the fluid is much hotter closer to the surface in Blundell. And that's because of the natural convection and the natural fractures which exist in that part of the rock. Whereas over here in the valley, for Fervo and Forge, we have basically a conductive gradient, which is not good for conventional geothermal, but again, good for EGS. That's what they were looking for. And in Project Cape, they're now doing 30, 40 stages of fracturing per well. This is from 2024. And July of last year, they did their first circulation test of Project Cape. And what you see here is they actually are achieving circulation rate between two wells of around 90 kilograms per second, which with 200-degree water, which is what they've got, gives them about 9.5 megawatts per well pair. And you can see how they've kind of arranged their wells here. They've got this so-called wine rack pattern. This is kind of looking in the gun barrel view of the horizontals. And they're distributed not only horizontally, but also with some vertical separation as well. And each one of those pads has 8 wells and will have a 33 megawatt power plant for a total of 100 megawatts for the three of them. So we're not talking about 1, 2, 3 megawatts anymore. We're now talking about 100 megawatts. And um, the first of those power plants will start up in January of 2026, a couple of months. And Fervo is now talking about continuing these patterns along northwards up the valley for a total of another 400 megawatts, making 500 megawatts in total. Now, I showed you this graph previously of the successes of Forge in improving their drilling speed. This is the experience of Fervo. So Fervo started out in Nevada in the Blue Mountain project, and this is what Blue Mountain had experienced previously in their drilling experience when they developed a conventional geothermal field. And those first 2 wells that Fervo drilled in Blue Mountain were kind of similar in experience. They were on the better side, but they're still taking 50, 60 days to drill, although to much greater depth or total length. But as they got better and refined their experiences and adopted some of the methodologies used in Utah Forge, you can see then that their drilling speed increased substantially, and they are now down in Project Cape, in some cases drilling in less than 20 days. So once again, that makes an enormous difference to the economics of the project. They had anticipated that they would do that. They planned that from the beginning. But the blue line is what their business model said that they hoped to achieve with the learning curve for drilling. And the green line is what they actually achieved, which was considerably better. The way that they did that was to switch over to use polycrystalline diamond compact bits, which are routinely used for oil and gas, but not commonly used for geothermal. It had been formerly kind of expected that geothermal couldn't afford to pay for PDC bits. But what they determined both at Forge and at Fervo was that although they cost more, they had a substantially greater drilling rate, and in the end they were cheaper. They had longer bit runs, they had faster penetration rates, and the net result is what you saw. And they experimented a lot with different cutter patterns, etc. They worked with the drilling bit manufacturers, and they refined them well by well and even bit by bit as they went through the process. Now, coming back to the map that I showed you before, or one like it that we developed at Stanford, I showed you the temperature. This is not a map of temperature, but it's a map of levelized cost of electricity. So that's the cost at which we anticipate you could generate electricity from EGS. And marked on the color bar on the right is $70 per megawatt hour. That's kind of the average price in the US. It varies a lot, but anyway, that's sort of mid-range. And so that's kind of orange color is what you would need. That's the place you could make money with EGS. It includes the western states, includes the Gulf Coast, but a lot of the country is blue. That, however, is based upon the cost of drilling in 2022 before Forge and before Fervo. If we take into account the substantially reduced drilling costs that they've achieved, not theoretically, but in practice, it changes the picture completely. The scale is a little different now, but I've still marked there the 70. And what you can see, this kind of straw yellow color, is where you could generate electricity for $70 a megawatt hour. And that's pretty much most of the lower 48. For some reason, West Texas doesn't look good, but the rest of it is pretty sweet, especially the western states, including where you are. Now, it's worth mentioning that the rest of the geothermal community was paying attention to what Fervo and Forge achieved, and conventional geothermal systems have now started to adopt some of these methods, including this one, which is in New Mexico in a place called Lightning Dock. And Lightning Dock was a project which had been developed actually for some time. They already had a 15 megawatt power plant there, but they couldn't get enough fluid to get it to work well. So it was basically a bust as a project. A company called Zanskar came in and adopted the drilling methodology from Fervo and Forge using PDC bits, etc. And what you can see there is that using those same kind of ideas, they were able to drill deeper and faster, and also they drilled larger diameter as well. And they were able actually to put that lightning dot project into operation with just one well. They had one well which produces 15 megawatts, whereas the original project had drilled about 10 wells without getting sufficient steam to or hot water to power that plant. So coming then to the overall, summary of where we were and where we are now, all of these issues have basically been overcome. So Fervo and Forge have uh, achieved the kind of rates that we need. They've been able to place the fractures over a wide area of or volume of rock by doing the multi-stage fracturing. It also turns out too that by making many smaller fracture treatments, that's less of an impact than making the one big, massive penny-shaped fracture, which is what they had attempted to do at Salts and some of those other places. So although there has been seismicity at both Fervo and Forge, it's all been at magnitude 2 and less, so people don't feel. And we have a commercial scale, a real scale power plant soon to go in operation at 100 megawatts in Project Cape. And this is what it looks like. They're in construction. There are three of them right now. You can see the valley with the wind turbines in the background, and these white patches are actually pig farms, but there are solar panels around there too. And this is when I visited there. So just to finish up in the last 5 minutes, um, with that map that I showed you that we developed of levelized cost of electricity nationwide, we looked at scalability. If you start picking off the good places, how far would you get? If you develop EGS everywhere and end up in West Texas, it's going to end up costing you more. But this is the scaling curve that shows as you increase the amount of development. And this arrow here, this red arrow, marks 1 terawatt. And 1 terawatt is sort of order of magnitude what the United States electrical grid capacity is today. And let me be clear, I'm not proposing that we completely, satisfy the grid with geothermal, but it's the question of how far could we go hypothetically. And what you can see is as a function of depth, or is it a function of all depth, which is the red curve, we can actually achieve, we could achieve, 1 terawatt at prices, levelized cost of electricity, cheaper than several other sources, and basically equivalent with solar PV without batteries. More expensive than wind, but basically cheaper than all of these others. And if we look at the capital costs, which is also important because the capital cost of geothermal is large because of the drilling and the construction and all the other things you have to do. Again, it's that changes the scale somewhat, but still makes it in the same ballpark as many of these other sources. And if we look at the DOE, Department of Energy's so-called liftoff report that they published earlier this year, what they show here is the original base when they started the study in 2021. This was their overnight capital cost per kilowatt of project. This one that they've indicated here is first of a kind, FOAK. That's basically Project Red, the one in Nevada, which cut that in half. And then over here, which they've marked as a liftoff target, they're not specifically referring to any particular project there, but that's basically what has been achieved by Project Cape, or will be when they start up in January of 2026. So overall, we've had a lot of geothermal activity worldwide. Everybody's interested in geothermal because it's a base load, clean, firm power, which a lot of people are looking for, especially nowadays for data centers. Um, the good geothermal energy, most of the projects that we have developed over the last 50 years worldwide in Kenya, places like that, they kind of grabbed all the good stuff already, and the more difficult projects are the ones which remain. So in order to get beyond that, EGS opens up new areas and new magnitudes of resource. And we have our first commercial EGS in operation already since October 2023. And because of the huge reduction in drilling costs, the overall attractiveness of EGS and competitiveness compared to other resources is now significant. I didn't mention this so far, but I will just in closing. Clean firm power is a good thing. Baseload power is a good thing, but it isn't all of what we need, especially in a grid which has a lot of intermittents like wind and solar. So one of the challenges for geothermal is that geothermal power plants don't like to be switched on and off. You can't kind of take the power when you want it. It's more like a nuclear plant. They just like to run 24/7. It's good for a data center, but it's not so good for uh, a town supply where people go to bed at 10 o'clock and turn everything off. So achieving dispatchability for geothermal is one of the kind of frontier areas that we're still looking at. So with that, let me go to a close and invite your questions. Thank you.
Great. Thank you, Dr. Horn. And maybe we can address a couple of the questions that did pop up in the chat before I'll give a little context for what's going on in Montana. I know someone asked earlier about the first 100 megawatts at Fervo, and if there's a customer, and it sounded like there is, if you could talk more about who's buying that and if we know how much they're paying for that.
Um, yeah, so I'm an engineer. I don't know too much about that, but anyway, it has been published publicly, at least some of the answers to that question. So the power purchase agreements have been signed, um, several of them actually. In fact, I think they have power purchase agreements for the first 500 megawatts already. So Google has taken some of it. Um, Southern California Edison has signed up for a large amount also, and three or four others, not all of whom I can remember. I think Shell, for some reason, signed up for some. The biggest PPA, however, is for Southern California Edison, although the first one was for Google. And Google actually bought the power from Project Red also in Nevada. And, again, we don't know the price, but, Southern California Edison is a public utility. So you know, they're under the control of the PUC in California. So um, they're limited to what they could pay for power. So we don't know what it is, but it can't be too much.
Right. Great. And it looks like there's more questions coming in. Maybe I'll jump in and talk a little bit about Montana, and then at the end we can try to address as much as we can
Okay.
of the other questions. So I'm going to share my screen, and this will just be really a cursory overview of what we're paying attention to right now. Can everyone see my screen? Yeah. So
Yes.
we've been keeping an eye on these developments with enhanced geothermal systems, and wondering, might this be a solution for Montana in the future? And this is just kind of a couple of things that we've been paying attention to. Starting just showing this is pulled from that Pathways to Enhanced Geothermal Liftoff report from DOE. But again, just showing an analysis of potential geothermal energy in Montana. Dr. Horn showed that slide of the kind of cost effectiveness across the states. And this is just kind of the ceiling of potential for enhanced geothermal that the Department of Energy determined for Montana. And you'll see that the coding here is that this red is kind of 50 to 100 gigawatts per region. And this is, of course, is the potential, and we're not going to be able to tap into that full amount. But all that to say, with Northwestern Energy's total average resource load or capacity requirement of 760 megawatts, there is a lot of potential for this in the state. And this slide is from a presentation that the Montana Bureau of Mines and Geology gave to the Energy Technical Advisory Committee, our interim committee of the state legislature. And they've been tasked since 2009 just to look at geothermal potential in Montana. And their presentation they gave earlier this year really didn't have a lot of this more up-to-date information about cost of EGS and drilling times and the depths that can be achieved. But they are looking at these different areas in Montana as potential areas of interest for geothermal development. And that's something that they presented. There's nothing necessarily developing there, but they're researching this, and this is on the radar. So with that, I mentioned there's this interest at that Energy Technology Interim Committee. They've been looking at what opportunities there might be for kind of opening the door to enhanced geothermal development, setting practical guardrails to make sure that should the developers come to Montana, they are coming on the right terms, and also have kind of certainty around what the mineral rights are and or whether or not their surface or mineral rights or some of those needs. So we've been working with legislators that are potentially going to be bringing draft legislation in 2027 around that, as well as I wanted to give just a sneak peek talking about Northwestern Energy's IRP. And this is a whole can of worms, so I'm just going to be clicking through things briefly. But suffice it to say, we're going to be talking a lot more about the IRP in the coming months, and we'll likely have a webinar in January to really talk about it. But let's just look at a sneak peek. Northwestern ran a bunch of modeling scenarios, and right now they're selecting to build more gas and nuclear energy. And there's a lot of nuance to this, and we're going to talk about some of the different model scenarios they ran. But it makes us wonder, what about geothermal in some of these scenarios, and what are some of the alternatives that might actually meet these needs at a lower cost and lower environmental impact? And this, like I said, we'll unpack more at a later time because they didn't model enhanced geothermal as a potential resource. And this, again, is just kind of over time. You can see that they still have their hydro. They have all this coal and then gas and really minimal wind and solar, which is its own issues in their modeling that we're going to talk more about. And then, of course, the emissions associated with these portfolios, where they just continue to have a lot of greenhouse gas emissions throughout the time frame. And that just leads me to wanted to show this slide that was from the Colorado Geologic Survey and a couple other groups showing the carbon intensity of different energy resources. And there's a lot here, and it's probably not the easiest to see, but over here we have binary cycle. Geothermal energy is the lowest carbon intensity per kilowatt hour generated. And if it can live up to cost projections and meet some of these goals and aspirations that it seems to be heading in the direction, perhaps it can be a cost-effective and also extremely low kind of life cycle embodied carbon resource that we're going to be pushing for to be at least modeled in the future IRP cycle that happens every 3 years. And again, this is from the DOE report, but just showing projections for building out gigawatts of enhanced geothermal capacity in the coming 25 years. And perhaps that can be included in projections in Montana. And finally, I also pulled this from their report, but this is, if it lives up to all the things they say it is, it could be a really good resource that has mitigatable environmental impact, really small physical footprint. It doesn't use fuel, so it's on site. You don't have to bring in fuel from elsewhere, and there's not cost associated with that. There's benefits of putting both infrastructure and workers to work from oil and gas industries, as well as all these other things that we are keeping an eye on to see if they can be that resource. But with that, I will give it back to questions and answers, and we can dive into some of the things that people are wondering about.
Yeah,
And
I
I
think
think, go ahead.
our next question is from David, and it's asking about seismicity and whether it's really just a PR concern or not.
No, it's a real concern. So, seismicity, as I said, has happened in a number of EGS projects with seriously bad consequences. There've been, um, particularly in Korea, in Pohang, they had hundreds of millions of dollars worth of damage and people were injured. So, I mean, this is very serious indeed. They produced a 5.5 earthquake in their project, which was attributable to the EGS project. There was no uncertainty about that. Um, so, it's a reality we have to face. It's not, however, you know, an insurmountable one. The point is, that we know lithium-ion batteries sometimes catch fire. That doesn't mean we abandon lithium-ion batteries. We, get on with our research to find out ways to stop them from catching fire. And that's the same has already been happening with EGS. Seismicity is an issue that is being addressed by many people, including in our research at Stanford, figuring out how to determine the risk factors for seismicity, and some of them are physical and some of them are geological. So you've got to understand the physics of how things work and understand the geology that you're actually in, and then go through also the development of the process to avoid seismicity if it starts to happen. So they've been following a process in Utah in Fervo and Forge, which is called a traffic light system. So they have um, continuous monitoring of the seismicity. If they start to feel something, then they back off. If they start to feel something more, then they stop altogether. And that's the kind of activity we actually know a lot more about induced seismicity now than we did 10 years ago, because of the experiences that have been gained from oil and gas. Um, Oklahoma, for example, is now seismically more active than California, because of the injection of wastewater from oil field operations. So it is an issue, but it's not uh, one which is not being addressed.
All right, we have a two-parter from Ben who had to jump, but I think they're really good questions. He's looking for
Okay.
examples of states that you would reference for model siting, permitting, and resource ownership frameworks.
Yeah. So again, I'm an engineer. I'm not a lawyer, but nonetheless, I see what's going on. I think to me, one of the shining examples from this point of view is the state of Nevada. So Nevada has had a very welcoming environment for geothermal, and that's one of the reasons why they enjoy so much geothermal electricity in the state of Nevada. They have many operating conventional geothermal projects in the state of Nevada, most of them quite small. They're 20, 50 megawatts, something like that, but they're spread all over. They have very many of them. So their legislature has been supportive of geothermal. A lot of US geothermal companies are actually based in Nevada, in Reno, because that's sort of their hearth and home. So, you know, Nevada is kind of a fine example of how legislation can actually stimulate an industry, as it has done in Nevada.
Great, that partially answers his follow-up question, but curious if you'd have anything else to add. about what priority actions for a state to take that could attract geothermal development. So you've mentioned legislation, but is there anything else you might think of? He mentions resource characterization, financing mechanisms, policy updates, etc.
Yeah, so I don't know honestly whether or not state of Nevada does things like that. I mean, we do have um, federal production tax credits for geothermal, which made a big difference um, in 2009 when it was first kind of turned on. Um, production tax credit was introduced for wind and solar 10 years before that, which gave rise to the expansion that we saw. And then it was also applied to geothermal in 2009, which actually gave rise to quite a significant expansion of developments in geothermal as well. So that's a mechanism um, to stimulate, commercial interest. In other countries, they've used feed-in tariffs. That's not been done in the US, but that has been effective, for example, in Germany. Although, you know, I have to be a bit skeptical about the ultimate cost of that in terms of the electricity. Um, anyway, they've successfully had a lot of projects that way. One of the issues that people will talk about a lot, which has actually changed recently with the current administration, is streamlining of permitting. So one of the issues with any kind of drilling operation is permitting and how many different agencies you have to deal with to get your permits and your water rights and land access and these kind of things. And we're seeing um, improvements in permitting time in a number of places. And of course, in that regard, the states actually have a lot to say as well, because you know the feds can do it on federal land, but a lot of geothermal developments may be on state land or on land which is regulated by the states.
Well, great. I think that takes us to the end of our hour here with Dr. Horn. Thank you so much for presenting to all of us. And we've recorded this, so it'll be available on our website. We're going to be working on a fact sheet around enhanced geothermal energy as well, enhanced geothermal systems. And we will keep an eye out as these things continue to develop um, and how it might play a role in Montana's energy landscape. Hope you all have a great night.
Great.
Thank you
Thank
very
you.
much.
Yeah.